So, today we're talking about PFAS. You've heard about this before, but let's recap shortly. Next slide, please. What are PFAS? Basically, oh, I forgot my props. Can you bring my props, please? I need my props. Basically, PFAS are molecules that have C atoms and F atoms bound to them. And they have a bunch of nice properties so that they can be used in a lot of everyday items also, for example, in shampoo or in the coated pans, the non-stick pans. But the nice properties that they have are also what makes them very desirable for use in the semiconductor industry. Next slide, please. However, they are not a very nice thing to have. So we have heard about all the negative influences on human health, on environmental health, and the fact that they accumulate in the environment, they don't really go away, ever. So that's why they are called forever chemicals. So really, one might think about that these PFAS chemicals, they should be banned, right? So that's what some of you might be thinking. But I'm going to tell you that this is not the full story. So next slide, please. We have, in this week, considered these devices. They are called CMUTs, so capacitive, micromachined ultrasonic transducers. Basically, it's a fancy way of saying loudspeaker in the ultrasonic range. This device, it kind of looks like a loudspeaker like you're used to. It has this plate, and this plate is vibrating. Also, this device, you can see it in this cross-section, but it's open to the atmosphere. So that's why because it needs to it needs this to work better. And this is also a problem, because when it's open to the atmosphere, everything that is in the atmosphere can enter the device. For example, water vapor. And we don't want that. So we have a kind of PFAS molecule that looks kind of like a spoon. This spoon, it has two ends. So it has this bottom end, this is like a head, and this tail. And this tail, you can think of as the C atoms and F atoms are bound to it. So this is like the F in the PFAS. And this head, it binds to the surface of this silicon device. Now you can imagine this spoon, it kind of looks like a bar, a spring maybe. And on a micro scale, this is actually what we're using it for. It's a spring, so that it doesn't stick to itself, this device. Also, this springy part, this fluorinated carbon chain, this is very water repellent, as you know, for example, from the cooking pans, the coated pans. And we don't want the water to get in contact because it might oxidize the silicon. It might also just sit on the surface and change the vibration. And we want it to produce a sound, an ultrasound, so we can't really have that. So next slide, please. So that's why we are using a process, a gas phase, vapor phase process, to coat our devices in this FDTS chemical, so basically in these little spoons. We have a machine. It consists of a reaction chamber and of a gas input line. And this gas input is measured precisely, but it's measured in terms of volume, and we need to do some calculations, and that's what we did. And we found out that one process step, this coating, takes 45 milligrams of this FTDS chemical. However, when we consider the surface area of the wafer that actually gets coated, also including the fact that the device, it has a kind of hollow structure and has some more surface area and geometry, we can find out exactly actually how much of this chemical is needed on one wafer. And as you can see, this is not a lot. This is 0.5 milligrams, so it's barely a fraction of what gets input there. So one could think, well, we had this in the other group, we could just bunch up the wafers into lots. But even if we do like the 25 wafers that could at maximum fit into these lots, we would have, I think, 10 milligrams about of stuff actually depositing on the wafers, but there's some excess. However, this excess is necessary. We cannot get rid of it because of the way the physics works of gases. When the pressure is reduced, when there's less gas, it doesn't work as well. So we are using this recipe always with the same amount of substance, so the 45 milligrams. This is a bit of a problem because the rest just gets exhausted by a vacuum pump, and it basically exits to the atmosphere. So now, what is 45 milligrams? When Fraunhofer is running this process, and they have been running it for a few years, and we have looked at the data since 2022, they used for these last 3 years a quantity that is about the size of your glasses, the little water glasses. or even less than that. So they used 10 grams. That's like a little flask. Next slide, please. And this is really nothing compared to, for example, the toxic amounts that you can intake. So if one coating uses 45 milligrams of this substance, you can compare it to, for example, the amount of substance that you consume while just drinking tap water here in Dresden. So if you drink 4 years of tap water, that's about the same intake as if you would just inhale all of the amount of this PFAS chemical in our process. And 45 milligrams, or even the integrated amount over 3 years, 11 grams, that's not a lot, really. So if we compare it, for example, to the total production in the world of fluorinated chemical substances, of course, the first one to think about is Teflon, so the fluoropolymers. The total production is in the kiloton range. So really, this is nothing. And this is important because the semiconductor industry is, of course, very important and dear to all of our hearts, and it needs these chemicals. Otherwise, without these little spoons to protect our devices from water, and also for other various important tasks, this cannot function. So really, we should not be thinking about banning these substances just in a blanket kind of way for all industries, but we should be smart about it. And this is what we had to say. Thank you for your attention.